Welcome back, class. In today's video, we're going to talk about some other phase changes. So we're going to talk about sublimation and deposition, and we're going to talk about melting and freezing. So let's start off with sublimation and deposition. So these are two, maybe you guys want to say, lesser known phase changes, right? So sublimation is the direct change between a solid and a gas, and deposition would be the change between a gas and a solid. So when molecules are in the solid phase, they have thermal energy, right, which allows them to vibrate. And so when surface molecules with enough of this vibrational energy, may be able to break free from the surface and become a gas, right? And this is similar to like a vaporization, where those surface molecules are breaking away from the liquid to become a gas, right? This is called, this is called sublimation. The recapturing of those vapor molecules into the solid, sort of analogous to condensation, right, is deposition. And the solid and vapor phases exist in a dynamic equilibrium if you keep it in a closed container, of course. If you leave it open, right, just like in vaporization, condensation, the gas will tend to flow away, and so the rate of sublimation will become much larger than the rate of deposition, and you'll start to see the solid disappear. And this is what typically occurs, right? So I can point out a couple examples of where we see sublimation kind of every day. Now, one of them that I think is probably that a lot of us have seen is with the sublimation of what's called dry ice, right? Or solid carbon dioxide, right? And solid carbon dioxide sublimes at a quite low temperature, right? It sublimes at minus 78 Celsius. So that means when we put it at room temperature, it sublimes quite rapidly, and we get that characteristic fog or smoke that we associate with putting dry ice, sitting dry ice out, or even putting dry ice into a liquid, which sort of escalates this, and you get that bubbling in that case, but we get the evaporation, or get the sublimation of CO2 gas off of the surface of the CO2 solid, the dry ice. But this process will also occur in regular ice, right? At temperatures below 0 degrees. So typically we put it at about minus 10, but when temperature is cold enough, right, when it's below 0, you can see this sublimation occur. So you could see this, for example, in the freezer, right? If you put ice cubes in a freezer, you will see that eventually those ice cubes will shrink in size. This is maybe particularly obvious if you have them in ice cube trays. This also will, in the wintertime, explain sort of why snow can slowly disappear, even when the temperature stays very cold. Right? If you have enough radiant energies from, say, like the sun, you can get sublimation of that ice without it ever that snow without it ever melting. Right? It just goes straight into the gas phase. And so there are other examples where we can see this sublimation of ice into gaseous water. So let's turn our attention to melting, though. So melting and freezing, right, is probably the other most commonly thought about, phase change, where you're changing between the solid and the liquid. Now, when those high energy liquid molecules, right, are lost from the solid, right, it loses its kinetic energy, right? So when that solid, when they have, again, some of the surface molecules of that solid have enough energy to transition into a liquid, right? They get more freedom, more kinetic energy, and they can now flow off of the solid as a liquid. Again, if energy isn't drawn back into the solid, right, the solid of that ice or whatever the solid will actually decrease in temperature. And this, again, energetically is just to show us that melting, just like evaporation, is an endothermic process. It requires energy because you're breaking down those intermolecular forces. And that means freezing is an exothermic process. So when you freeze like water, it actually gives off heat, right? And this is why, just to think about it in a practical application, this is why we can't just have our freezer, and just have it sit there, right? You think about a cooler, right? You can get it really cold, but if you let it sit long enough, right, the ice is going to melt, it's going to raise back up in temperature. Because the process of freezing, right, actually gives off temperature, always gives off heat. And so the only way that your freezer stays cold is if you continually to keep it cold, right? Then you run a condenser, right? Or you pull out the heat as it's formed to keep the freezer cold. Otherwise, your freezer would eventually warm up. Even as you put warm things in to a cold, right? As they cool down, again, they're going to give off heat. Okay. So melting requires input of energy to overcome the attractions in the solid, in the same way that freezing releases energy as you develop those new attractions. And the amount of heat required to melt a mole of solid is called the heat or the enthalpy of fusion. Now, the term fusion is sometimes confusing. Fusion is just the scientific term for melting, right? So we call it melting. Scientifically, a lot of the force is required as the fusion. So we call it the heat of fusion, right? Very similar to the heat of vaporization in the sense that it's always going to be a positive value because it's endothermic. Again, it's somewhat temperature dependent, just like delta H of vaporization. And it's generally much less than the delta H of vaporization. Meaning, if we have a material, the transition between the liquid and the gas takes a lot more energy than the transition from the solid to the liquid. And the big reason there is that to go from the liquid to the gas, you have to break every intermolecular force, right? You have to totally separate the molecules. When you go from the solid to the liquid, you just have to weaken those intermolecular forces. You don't have to totally break all of them because remember, in the liquid, the intermolecular forces are still there. They're just now a little bit weaker. And so it doesn't require nearly as much energy to melt as it does to vaporize. And so heats of fusion are quite a bit less than heats of vaporization. And you can see that, you can see from our table here that the heat of fusion for water, right, is about 6 kilojoules. Remember, the heat of vaporization was about 40 kilojoules, so quite a bit less. Now, the delta H of crystallization or freezing is, again, the opposite of the delta H of fusion. And we didn't talk about it, but if you did want to come up with a enthalpy of sublimation, it would simply be the two processes combined. Because sublimation is going all the way from a solid to a gas, right? The energy required is going to be what the sum of the heat of fusion and the heat of vaporization is for that material. So it's sort of the additive of the two processes there. So let's compare heats of fusion, heats of vaporization. So we saw water, and here you can see visually where this is a consistent trend where, heats of fusion are quite a bit lower than the heats of vaporization. And again, it just doesn't take as much energy to go from a solid to a liquid as it does to go from the liquid to the gas. Now, previously we looked at a heating curve to look at the boiling or the vaporization process. Well, here we can look at a similar heating curve to look at the melting process, where you're starting with a solid here and you're heating it up to melt it. So as you heat it, right, the temperature again increases linearly until you reach that melting point. And on those diagonals, just like we saw in vaporization, you can use our standard heat equation to calculate how much energy it takes to raise the temperature, how much heat it takes to raise the temperature up to the melting point. Now, once you reach the melting point, you see again another flat region of the curve. Again, this is characteristic of when we see those phase changes. So temperature doesn't change while the phase change is undergone, while we're undergoing the phase change, right? Because all of the energy we input is going into breaking down the intermolecular forces, not increasing the temperature. So to calculate the heat required for the flat portion, right? Again, we're going to use a similar to what we did in vaporization, where we're going to take the number of moles that we're melting and times it times the enthalpy of fusion to see how much energy it would take to melt that amount of substance. And once all the solid has been melted into a liquid, then again we can start that increase in temperature up till eventually the boiling point, right, that we would reach. So this is a key in sense once is like excuse me, while we have both phases present, the temperature will always be, basically the same, right? So once the solid is turned into liquid, the temperature can start to rise again. So ice water, right? If you have both ice and water present, you will always be at that 0 degrees if you're at 1 atmosphere. So ice water is not gonna, as long as there's a significant amount, a reasonable amount of ice present, is still gonna hover around that 0 degree mark. And then, but once all the ice is gone, then that liquid can start to more rapidly increase in temperature. So in this last section of the video here, I want to look at the overall heating curve of water and want to do some calculations to see how we would go about calculating the heat required for each one of these segments of the heating curve. So if we take a sample all the way from 1 here, all the way from a piece of ice, in this case we're at minus 25 degrees, all the way through our melting point, and then up to our boiling point until we're at steam at some temperature above 100 degrees, how much energy will it take to do that? Now, the key here is we can't do it all at once. We have to break this down into steps because remember, the diagonal, right, segments of the line are going to be calculated using our normal heat equation, but whereas points 2 and 4 are going to utilize our delta H's, right? Whether it's our enthalpy of fusion to do the melting or enthalpy of vaporization to do the boiling. So we have to do this in 5 steps. So let's walk through each of those segments and the math involved. So first of all, step 1. Now, for simplification of the math, we're looking at 1 mole of material. And so, our number of moles is just going to be 1. And so we can sort of make it standard. We can easily do the math here. So in this first segment, we're starting with ice at minus 20, and we're heating up to the melting point, or 0. So since this is one of the heating phases, right, we're changing the temperature, we're going to use our normal Q equation. So Q is going to equal the mass of our water. We've got 1 mole, so that's about 18 grams. We look up the specific heat now. I will note here, make sure if we're doing this that you use the specific heat of the phase that we're looking at. So in this case, we're heating up ice So we need to use the specific heat of ice, right, which is going to be different than the specific heat of liquid water or steam. And so our equation is going to be their mass, 18 grams, times our specific heat of ice, times our temperature change. Now remember, temperature change is always final minus initial. So we get 0 minus a minus 25 degrees, or 0 plus 25 degrees. So we got a change of positive 25 degrees here. So which tells me that my Q is going to be positive, right? I have to input heat here. So it's going to, heat has to be added. So to transition over this segment of the curve, it takes 941 joules or 0.941 kilojoules. Now, our second segment, right, is going to be the melting segment, right, that flat portion. So to melt 1 mole of ice at 0 degrees is going to take the following amount, right? So we're going to use this equation, right, utilizing our delta H of fusion. So we have 1 mole, so that's nice and easy. You look up the delta H of fusion for ice, for water, 6.02 kilojoules per mole. So if I do the math, to melt 1 mole of ice at 0 degrees, it's going to take 6.02 kilojoules. So now we're at where we've fully melted the ice. So we have liquid water at 0 degrees. So to heat that liquid water from 0 degrees up to the boiling point, 100 degrees, again, we're going to utilize our standard heat equation, utilizing the same mass, but now the specific heat of liquid water, and our temperature change of our T final, 100 minus 0, so 100 degree temperature change. So we get 18 times 4.18 times 100, we get 7.52 times 10 to the third joules, or 7.52 kilojoules. So notice, so far this is the most energetically intensive part, right? To heat up that water, those 100 degrees, took 7.5 kilojoules, right? That's more heat than it took to melt the water. And then finally, now we need to boil that 1 mole of water. So we're going to use our mole of water. We're going to look up our heat of vaporization for water. Notice it's 40.7 kilojoules. So do the math. So to boil that water, again, much more energetic, right? It took 40.7 kilojoules to break all those intermolecular forces. To get, now at this point, we are at 1 mole of steam at 100 degrees. So just to kind of see how we do it, we're going to also increase that temperature, that steam, from 100 degrees up to 125 degrees. And how much energy would that take? Again, we have our mass of 18 grams. We use the specific heat of steam. Now notice steam is a lot easier to heat up than liquid water. And our delta T, which is just going to be 25 degrees. And so we're going to do our math, and it takes 900 joules, or about 0.904 kilojoules, to heat this up. So now, if we go back to our slides and we keep track of our numbers, right? So we got 0.941 and 6.02. So we got 0.941 kilojoules plus 6.02 kilojoules. And if we look at the third phase, that was 7.52 and 40.7. 7.52 plus 40.7 kilojoules. And we add that to the last one, which was 0.904 kilojoules. So if we take this and add up all of those numbers, we'll get to how much energy it takes to make the overall change. And so we got 0.941 plus 6.02 plus 7.52 plus 40.7 plus 0.904, end up with 56.09 kilojoules is what it took to take a mole of water and take it from minus 25 up to 125 through these different segments of the heating curve, right? Took about 56 kilojoules. Noticing that the vast majority of heat was involved in the boiling of the water, right? The rest of it took, about 16 kilojoules, right? All the other heating up, changing the temperature, and melting it took, less than half of what it takes to boil it. So just a little idea about the energetics involved in, what you have to do with, breaking all those intermolecular forces when you boil. It takes a lot of energy compared to the other processes, just changing the temperature or, melting. All right, so that wraps up this segment or this video. In the next video, we're going to be turning our attention to talking about liquids in a more, qualitative way. And we're going to talk about something called phase diagrams and some other general properties of liquids.